Right now, somewhere over the ocean, an aircraft is holding 400 people 6 miles in the air, and the calculation keeping them there rests on an equation nobody has ever proven works. Not proven it is hard to solve, proven it works at all. The same equation forecasts your weather. Your cardiologist uses it to model the blood moving through your heart this second. And yet the people who understand it best, some of the most formidable minds of the last 200 years, have quietly conceded that it beats them. Heisenberg helped split the atom, but said fluids were the harder problem. Feynman called it the most important unsolved question in all of classical physics, then moved on, because he could not answer it either. So there is a wound at the centre of the physics of everything that flows, and it has stayed open since 1822, when a French engineer wrote the equation down without understanding why it was right, in the very years his masterpiece bridge cracked and was torn down in the heart of Paris. Tonight, we follow that one equation out of that collapse. Through a mathematician who hid his own genius inside a prison camp, past $1 million bounty that has gone unclaimed for 26 years, all the way to a machine made of water that copies itself smaller and faster until it tears a hole in reality. So settle in, and if you are new here, subscribe or join so the next one finds you. There is a Patreon as well, where these dives run longer and stranger across space, physics, math, and the questions nobody ever managed to finish. Stay to the end, because by the time we get there, you are going to understand that every breath you are taking right now is a problem no one alive can solve. Let's start where it started. There is a single equation that describes the motion of every fluid on Earth, the air sliding over the wings of the last plane you flew in, the blood moving through the 4 chambers of your heart in the time it takes you to read this sentence, the water in every river, the churn of every ocean, the cream folding into your coffee this morning, the weather that will roll over your city tomorrow. One set of equations governs all of it. Engineers around the world solve it billions of times a day. It has kept passenger aircraft in the sky for the better part of a century. And here is the fact that almost no one outside of a few hundred mathematicians on the planet actually knows. Nobody has ever proven that it works. I do not mean that it is difficult to solve, although it is. I mean something much stranger and much worse. We do not know if the equation that runs modern civilization even has answers. We do not know whether, for some perfectly ordinary starting condition, some gust of wind or swirl of water that could occur in the real world, the equation quietly breaks, produces nonsense, hands back infinity where there should be a number. We have been using it for 204 years, betting hundreds of millions of lives on it, and we cannot prove that it does not, under conditions we have not yet tried, simply fail. In the year 2000, a private institute in Cambridge, Massachusetts, offered $1 million to anyone who could settle the question one way or the other. Just tell us, they said. Tell us whether this equation always has a sensible solution, or find us the single case where it doesn't. That was 26 years ago. The money is still sitting there. Of the 7 problems they put that bounty on, 6 remain unsolved, and this is the one that working scientists use every single day without knowing whether it is true. You have been taught, if you were taught anything about this at all, that physics is a mostly finished project, that the hard part was Einstein and quantum mechanics, the exotic stuff, the very fast and the very small, and that the ordinary world, the world of water and air and weather, was nailed down centuries ago by men in wigs. That is the version that gets told. It is comforting, and it is wrong. The truth is that the physics of a glass of water, the actual mathematics of what happens when you stir it, is one of the great open wounds in human knowledge. And the people who understand this best have made a quiet peace with the fact that they may not solve it in their lifetimes. Some of them are not sure it can be solved at all. What I want to show you over the next couple of hours is not just that this problem is unsolved. Unsolved problems are cheap. What I want to show you is why it is unsolved, which is a far more disturbing thing. Because the reason has nothing to do with a lack of effort, and everything to do with a possibility that sits inside the equation like a splinter. The possibility that reality, ordinary fluid reality, the reality of your own blood and breath, can spontaneously manufacture infinity out of smoothness. In finite time, from a perfectly calm beginning, and that we have no way, none, to prove it can't. That possibility has a name in the field. They call it blow-up. Hold on to that word, because by the time we get to the bottom of this, you are going to understand that the question of whether fluids can blow up is not an abstract curiosity for specialists. It is a question about whether the mathematics that describes the world you are living in is complete, or whether it is hiding a wound at the very centre of things that no one has been able to close since 1822. And I need you to see how we got here, because the story of how we got here is, I promise you, stranger than the equation itself. It begins with a bridge that fell down. In the 1820s, Paris was trying to build the most beautiful bridge in the world. It was going to cross the Seine near the Hôtel des Invalides, roughly where the gilded Pont Alexandre III stands today, and it was going to be a suspension bridge, which in that era was cutting edge, almost science-fictional technology. The span was around 155 metres. The design called for cast iron towers decorated with Egyptian motifs, which were very much in fashion in France after Napoleon's campaigns, and the man given the job of designing it was a 40-year-old engineer named Claude-Louis Navier, who was, at that moment, considered one of the finest mathematical minds in the entire French engineering establishment. You need to understand who Navier was, because the irony of what happened to him is almost too neat to be real. He was born in Dijon on the 10th of February, 1785. His father, a lawyer to the Legislative Assembly, died when Navier was 8 years old, and the boy was raised largely by his great-uncle, Millennium Prize, who happened to be one of the most celebrated civil engineers in France, a builder of canals and bridges. So Navier grew up inside the world of stone and iron and load-bearing calculation. He was not, at first, obviously brilliant. When he took the entrance examination for the École Polytechnique in 1802, the great engineering school of the French state, he was admitted in 116th place. Out of 117. He was, on paper, the second worst student they let in. And then something happened to him, the way it sometimes happens to a certain kind of mind that just needs the right key. Within his first year, he had climbed into the top 10. He fell under the influence of Joseph Fourier, the mathematician whose work on heat would echo through the next 2 centuries of physics, and Navier absorbed from Fourier a conviction that would define his whole career and eventually destroy his reputation. The conviction was this: that the physical world could be captured in mathematics, not approximated, not sketched, captured, that if you were rigorous enough, precise enough, mathematical enough, the equations would tell you the truth about steel and stone and water more reliably than any craftsman's intuition ever could. That belief made him a revolutionary in engineering. He is, with some justice, called one of the founders of modern structural analysis, the discipline that lets you calculate whether a beam will hold before you build it. But that same belief is the thing they would use against him when the bridge came down. Construction on the Pont des Invalides began in 1824. By 1826 it was nearly finished, an elegant thing of iron and cable stretched across the river, and then, just before completion, a water main burst. Some accounts say it was a sewer. Either way, water flooded the ground around one of the supporting anchorages, the earth shifted, and one of the towers cracked and began to tilt. And here is the part that matters. The damage was, by most technical assessments at the time, minor, repairable. Early estimates put the cost of fixing it at something like 1 or 2% of the total contract. This was not a catastrophic structural failure. It was a burst pipe and some subsidence. But the Municipal Council of Paris had never wanted the bridge. It had been controversial, expensive, a project pushed through over local objections, and the crack gave the council exactly the excuse it needed. They seized on it. They forced the question of whether the whole thing should be torn down. And a government committee was convened to render judgment, not just on the bridge, but implicitly on Navier himself. And the judgment they handed down is one of the quietly cruel documents in the history of engineering. They criticised Navier for relying too much on mathematics. They praised, by contrast, the more empirical, more hands-on, less theoretical approach of the British bridge builders. Men like Thomas Telford and the Stephensons, who trusted their gut and their experience over the equations. Think about what that meant to him. The one thing he had staked his entire life on, the belief that mathematics was the deepest and truest description of the physical world, was now being cited in an official government report as the reason his bridge had failed. The bridge was dismantled in 1827. It was, by every account, a public humiliation. It followed him. 15 years later, the novelist Honoré de Balzac was still using it as a cultural reference point. In his 1841 novel Le Cœur du Village, Balzac writes of, and I am translating here, the disaster which happened in the heart of Paris to the first suspension bridge built by an engineer. A member of the Academy of Sciences. He does not even need to use Navier's name. Everyone knew. The engineer who trusted the math. The bridge that fell. Now here is where the story turns, and where you start to feel the strange gravity of this whole subject. Because in the very same span of years that Navier was designing the bridge that would humiliate him, he was also doing the work that would make him immortal, and he had no idea. In 1822, 2 years before construction on the bridge began, Navier presented a paper to the French Academy of Sciences. It was about the motion of fluids, and buried in that paper was the equation. The equation we still use today, the one that describes the air over the wing and the blood in the heart, and the weather over the city. He wrote it down in 1822, and it was correct, and it is still correct, and it will be correct long after everyone alive today is dead. And he got it right for reasons that were completely, embarrassingly wrong. This is the part that I genuinely find hard to get my head around, and I have read the history of it more times than I would like to admit. To understand why Navier's derivation was wrong, you have to understand what he was trying to do. He wanted to describe a real fluid, a fluid with friction, a fluid that resists being sheared, which is what separates honey from water, and both of them from the idealized frictionless fluids that mathematicians had been playing with for the previous 70 years. And to build that friction into his equations, he reached for the most fashionable idea in French physics at the time, which came from Pierre-Simon Laplace and his circle. The idea was that everything, all matter, is made of tiny discrete molecules, and that these molecules exert forces on each other, forces of attraction and repulsion that depend on the distance between them. So Navier imagined the fluid as a vast collection of these little particles, and he reasoned as follows. When two neighbouring molecules are moving at different velocities, when one is sliding past another, the repulsive force between them changes. He assumed it changed in proportion to the difference in their velocities, scaled by some function of how far apart they were, and he summed up all these little intermolecular pushes across the whole fluid, turned the sum into an integral. and out came a term describing internal friction. Out came viscosity. The problem is that essentially none of that is right. Fluids are not well described by that molecular force model. The specific mechanism Navier proposed, molecules pushing on each other with a velocity-dependent repulsion, is not how viscosity actually works. And the constant that emerged from his derivation, the number that controls how thick or thin the fluid is, was to Navier essentially meaningless. In the beautiful phrase of the mathematicians Marco Cannon and Susan Friedlander, who wrote about this history, it was for him a mere adherence constant, a function of molecular spacing to which he attached no particular physical significance. He did not know what his own viscosity term meant. He had derived the correct equation for the wrong fluid using the wrong physics, and he could not have told you what the most important number in it actually represented. His contemporaries noticed. Simon Denis Poisson, one of the great mathematical physicists of the age and a purist about molecular theory, attacked Navier's derivation, pointing out that the leap from a discrete sum of molecular forces to a smooth continuous integral was not justified, that Navier had waved his hands over exactly the step that mattered. And Poisson was, in the narrow technical sense, right. Navier's reasoning did not hold up, and yet the equation, the thing the reasoning produced, was true. It described real water and real air with a precision that Navier had no right to expect and could not explain. There is a paper written in 2003 for the Notices of the American Mathematical Society by those same two mathematicians, Cannon and Friedlander, and its title is the reason I keep coming back to this story. They called it Navier, blow up and collapse. On the surface, the collapse is the bridge and the blow up is a bit of mathematical wordplay. But once you know where this whole subject is heading, once you understand that the deepest open question about Navier's equation is literally whether its solutions can blow up, whether they can collapse into infinity, that title stops being wordplay. The man whose bridge collapsed in the heart of Paris wrote down the equation that, 2 centuries later, we cannot prove will not collapse on us. Hold that. We are going to come back to it, and when we do it is going to mean something it did not mean the first time. Navier never knew what he had. He was admitted to the Academy of Sciences in 1824, the same year the doomed bridge broke ground. He was made a Chevalier of the Legion of Honour in 1831. That same year he took over the chair of calculus and mechanics at the École Polytechnique, stepping into a post vacated by Augustin Louis Cauchy, who had gone into political exile. He died in Paris on the 21st of August 1836, at the age of 51, remembered mostly, in his own time, as the engineer whose bridge came down. His name is now inscribed on the Eiffel Tower, one of 72 names of French scientists and engineers cut into the iron, and almost no one who reads it knows that it belongs to the man who wrote the equation for everything that flows. But Navier's flawed derivation left the field with a problem. The equation was right, but the reasoning underneath it was rotten, and everyone knew it. You cannot build the future of a science on a result that was obtained by accident, on a molecular model that its own author could not defend. Someone was going to have to derive this thing again properly, from foundations that would actually hold. And the man who did it was, in almost every respect, Navier's opposite. Where Navier was punished for trusting mathematics too much, this man would spend 54 years in the most famous mathematics chair in the world. Where Navier died in relative disappointment, this man would die loaded with honours, a Knight of the Realm, a Member of Parliament, having outlived nearly everyone who had ever doubted him. His name was George Gabriel Stokes, and to understand what he added to the equation, you first have to understand what was missing from the world before Navier, in the frictionless fantasy that the greatest mathematician of the 18th century had left behind. To find the ghost in the machine, you have to go back to 1755 to Berlin. to a man who was arguably the most productive mathematician who has ever lived. Leonhard Euler presented a paper that year to the Prussian Academy of Sciences with the plain title Principes Normaux du Mouvement des Fluides, General Principles of the Motion of Fluids. It was published in 1757. In it, Euler wrote down the equations for the motion of an ideal fluid, a fluid with no friction at all, no viscosity, nothing to resist the sliding of one layer over another. These are the Euler equations, and they are the direct ancestor of everything we are talking about. They are Navier's equation with the friction switched off, and they produced a result so obviously insane that it became one of the most famous embarrassments in the history of physics. It is called D'Alembert's paradox, after Jean-Laurent D'Alembert, who ran into it around the same time. Here is the paradox. If you take Euler's frictionless equations and use them to calculate the drag on a solid body moving through the fluid, a ball, a wing, the hull of a ship, the answer that comes back is 0. Not small. 0, the equations say that a body moving through an ideal fluid experiences no resistance at all. Which means, if the equations described reality, that an aircraft would need no engines, a ship would need no propulsion, an arrow fired into the air would never slow down. Everyone could see this was absurd. You can feel the drag of air when you stick your hand out of a car window. The frictionless equations described a world that does not exist. The missing ingredient was viscosity. Friction, the thing Navier had, by accident and bad reasoning, managed to build into his 1822 equation. So by the middle of the 19th century, the situation was this. Euler had given the world beautiful, rigorous, frictionless equations that were provably useless for real fluids. Navier had given the world the correct equation with friction included, but by a derivation that no serious mathematician could accept. What was needed was someone to derive the viscous equations again, cleanly, from principles that would survive scrutiny. And that someone was born in a rectory in Ireland in 1819. George Gabriel Stokes was born on the 13th of August 1819 in Skreen, a village in County Sligo on the wild Atlantic coast of Ireland. He was the youngest of 6 children of a Protestant clergyman, and the household was drenched in religion. All 3 of his older brothers became priests. This matters not as trivia, but because Stokes carried a deep, sincere, lifelong Christian faith through a career at the absolute frontier of mathematical physics. And he saw no contradiction in it, and it shaped the almost monastic steadiness of the man. He did not have Navier's dramatic reversals. He had instead something rarer. Consistency, a stayer's temperament. 54 years of it. He went to Cambridge, and in 1841 he graduated as Senior Wrangler, which is the title given to the single top student in the entire mathematics examination, the Tripos, in a given year. In Victorian Cambridge, being Senior Wrangler was a form of national celebrity. Crowds would gather to hear the results read out. Stokes was first, and he was also the first Smith's Prizeman, another top mathematical honour, in the same year. And then in 1849, at the age of 30, he was appointed to the Lucasian Professorship of Mathematics. I want you to understand what that chair is. It is the professorship that Isaac Newton held. It is the professorship that much later, Stephen Hawking would hold. There is arguably no more storied seat in the history of science, and Stokes held it from 1849 until his death in 1903. 54 years. It is the longest tenure of any Lucasian professor in the history of the position. Longer than Newton, longer than anyone. When people talk about the giants whose shoulders science stands on, they are usually talking about people who had one great explosive decade. Stokes had a half-century of quiet, relentless, foundational work, and one of the first things he did in that chair was fix Navier's equation. In 1845, 4 years before he got the Lucasian chair, Stokes published a paper called On, the Theories of the Internal Friction of Fluids in Motion. And in it, he did what Navier could not. He derived the viscous flow equations from clean continuum principles. He deliberately refused to assume anything about molecules. He did not need Laplace's little particles pushing on each other. He treated the fluid as a smooth continuum, infinitely divisible, and he asked only what symmetries and what physical requirements the internal friction of such a continuum must satisfy. And out came the same equation Navier had written 23 years earlier. But now it stood on foundations that would not crack. And crucially, Stokes understood what the viscosity term actually meant. To him, it was not a mysterious adherence constant. It was a real, physical, measurable property of the fluid, the magnitude of its internal friction. He knew what his own equation was saying, which is more than Navier ever did. This is why we call them the Navier-Stokes equations. Two men, 23 years apart, one who found the answer without understanding it, and one who understood it well enough to prove it, and it is worth pausing on the injustice buried in that name, because there were others. A French engineer named Admar Jean-Claude Bar de Saint-Venant published his own derivation in 1843, 2 years before Stokes, and his version explicitly applied to turbulent as well as smooth flow, which was arguably ahead of its time. Poisson had a version in 1829, Cauchy had touched it in 1823. The equation was, in a sense, discovered 4 or 5 times over by people reaching for the same truth from different directions, and history compressed all of that into 2 names. St. Venant, in particular, has a real claim to have gotten there before Stokes, and almost no one remembers him. That pattern, the person who was right and early and forgotten, is going to come back in this story. It comes back more than once. Keep a mental note of it. Now I need to actually show you the equation, or rather what the equation says, because everything that follows, all the horror and all the beauty of the next 200 years, lives inside one specific piece of it. I am not going to make you read symbols. I am going to tell you what it means, because the meaning is where the danger is. At its heart, the Navier-Stokes equation is nothing more exotic than Newton's second law, force equals mass times acceleration, applied to a tiny parcel of fluid. That is it. It says that if you follow a little blob of water as it moves, its acceleration is determined by the forces acting on it. There are only a few forces. There is pressure, the fluid getting pushed from regions of high pressure toward regions of low pressure. There is viscosity, the internal friction Stokes formalized, which tends to smooth things out, to drag fast-moving fluid and slow-moving fluid toward a common speed, to erase differences. There might be an external force, like gravity. And then there is one more term, and that one more term is the whole problem. It is the reason we are here. That term describes the fluid carrying itself. It is called the convective, or advective, or nonlinear term. And what it captures is the fact that a fluid transports its own motion. The velocity of the fluid is what moves the fluid, and the fluid it moves has its own velocity, which then moves more fluid. The motion feeds on itself. In the language of the mathematics, the velocity gets multiplied by itself. The equation is nonlinear, and that word, nonlinear, is one of the most important and most feared words in all of science, because nonlinear systems are the ones that can run away from you. Linear systems are gentle. Double the input, and you double the output. Nothing surprising. Nonlinear systems can take a small input and amplify it without mercy, can feed their own output back into themselves and spiral, can turn the smooth into the chaotic. Every hard problem in physics, from weather to turbulence to the chaos that makes long-term prediction impossible, lives in that word. There is one more feature of the equation I have to give you, because it is quietly one of the eeriest things about it, and almost no popular account will tell you. For most of the fluids we care about, water and air at ordinary speeds, we treat the fluid as incompressible, meaning it cannot be squeezed, its density cannot change. Push on it here and it must move there, instantly, because there is nowhere for the extra to go. And to enforce that, the equation needs the pressure to do something remarkable. At every instant, the pressure everywhere in the fluid has to adjust itself, all at once. Across the entire body of water or air, to exactly the values that keep the fluid from compressing anywhere. Mathematically, the pressure at any point is determined by what the whole rest of the fluid is doing, everywhere. Simultaneously, it is what the mathematicians call a non-local, instantaneous constraint. A change in the flow in one corner requires the pressure in every other corner to respond in the same instant. I want you to feel how strange that is. In the idealized incompressible equation, every single point of the fluid is in instantaneous contact with every other point. The whole fluid is, in a sense, holding itself together as one object, informed everywhere at once about what is happening everywhere else, with no delay, no travel time. It is an idealization, of course. Real fluids are slightly compressible, and the influence actually travels at the speed of sound. But the equation we use, the one civilization runs on, the one we cannot prove has solutions, describes a fluid whose every part is aware, instantly, of every other part, and that instantaneous whole-body coordination is part of what makes the mathematics so brutally hard, because you can never isolate one region and study it alone. Every point is entangled through the pressure with the entire rest of the flow. The fluid does not have parts. Really, it has one continuous, self-referential, instantly communicating whole. And the nonlinear term is that whole feeding on itself. So look at what the Navier-Stokes equation actually is. It is a tug of war. On one side, viscosity, the smoothing force, the friction that wants to calm everything down, to spread motion out evenly, to kill sharp differences. On the other side, the nonlinear term, the self-feeding force. The part of the fluid that grabs its own motion and concentrates it, that can take energy spread across a large calm region and funnel it into a smaller and faster and more violent one. The entire 2-century mystery comes down to a single question about that tug of war. Can the nonlinear term ever win completely? Can the self-concentration outrun the smoothing so badly, so totally, that the fluid drives its own velocity to infinity in a finite amount of time before viscosity has any chance to catch up? That is blow up. That is the whole thing. And when Navier and Stokes wrote the equation down, nobody was asking that question, because it did not occur to anyone that a smooth, gentle, well-behaved fluid could do something so violent. For almost 90 years after Stokes, the equation sat there, useful and trusted and unexamined at its foundations, while engineers used it to build ships and mathematicians assumed, without proof, that of course it behaved itself. Of course a smooth start gives a smooth flow. Why would water suddenly go insane? And then, in 1934, a Frenchman looked hard at the equation and realized that nobody could actually prove that it wouldn't. His name was Jean Leray, and he is the man who turned a comfortable assumption into a terrifying open question, and he did it with a single paper that essentially founded the entire modern mathematical theory of fluids. Leray was born on the 7th of November 1906 in a small town near Nantes in western France. He was trained at the École Normale Supérieure, the most elite scientific school in the country, finished his doctorate in 1933, and in 1934 he published a paper in the journal Acta Mathematica, volume 63, with the title Sur le mouvement d'un liquide visqueux emplissant l'espace, on the motion of a viscous liquid filling space. It is one of the most important papers in the history of applied mathematics, and to understand what it did, you have to understand the trap Leray walked into and the extraordinary, honest, unsettling way he chose to walk out of it. Leray wanted to prove that the Navier-Stokes equations have solutions. Just that. Give the equation a smooth starting state, some initial pattern of fluid motion, and prove that there exists a solution that tells you what the fluid does at every moment afterward. This is the most basic thing you can ask of an equation that is supposed to describe reality. If it does not have solutions, it does not describe anything. And Leray discovered that he could not do it. Not because he was not brilliant enough. He was one of the outstanding mathematicians of the 20th century. He could not do it because the nonlinear term, that self-feeding beast at the center of the equation, would not let him keep control. Every time he tried to guarantee that a smooth solution would continue to exist for all time, the mathematics slipped out of his hands at exactly the small scales where the nonlinear term concentrates energy. He could not rule out the possibility that the solution would develop a singularity, a point of blow-up, where the velocity or its rate of change becomes infinite and the whole description falls apart. So Leray did something radical, something that tells you everything about how deep this problem runs. He changed the meaning of the word solution. If he could not prove that a proper, smooth, everywhere well-behaved solution exists, he would prove that a weaker kind of object exists. He invented what we now call a weak solution. A weak solution is a fluid flow that satisfies the equation in an average smeared-out sense, but which is allowed to be rough, allowed to have points or moments where it is not smooth, where you cannot take the derivatives the original equation seems to demand. He loosened the definition of solution until he could guarantee that something existed, and he proved, brilliantly, that these weak solutions always exist, for all time, in 3 dimensions, for any reasonable starting condition. That result stands to this day. It is bedrock. But look at the price he paid, because the price is the whole story. Leray called his weak solutions turbulent solutions, and he was quite explicit in the paper about what he had given up to get them. He could not prove they were unique. He could not prove that a single starting condition leads to a single future. He could only get his existence result, in his own words, by dispensing with the regularity of the solution at certain instants. Read that again slowly. In order to guarantee that his fluid equation had any solution at all, he had to accept that at certain moments in time, the solution might stop being smooth, might develop a singularity, might, in a word, blow up. He could not prove it happened. He could not prove it didn't. He built his entire existence theory on a foundation that explicitly left the door to catastrophe open, because he could not find a way to close it. I find this genuinely moving, and I want to sit with it for a second, because it is the exact opposite of how we are taught science works. We are taught that the great figures nail things down, that they replace uncertainty with certainty, that progress means closing questions. Leray's monumental contribution was to open one. He took a problem everyone assumed was fine, and he proved, rigorously, that we do not know if it is fine, and he was too honest to pretend otherwise. He is the man who found the wound. Everything since has been the attempt to close it, and nobody has. And then, 6 years after that paper, the German army came across the French border, and the story of the man who gave up smoothness took a turn that is almost unbearable in its symmetry. When France fell in June of 1940, Jean Leray was an artillery officer. He was captured, and he spent the next 5 years, from 1940 to 1945, as a prisoner of war in a camp called Auflag Svi A at Edelbach in Austria. Now here is what a lesser man would have done. He would have kept his head down and waited. Here is what Leray did. Leray was one of the world's foremost experts on fluid dynamics, on the mathematics of flow, and he understood with total clarity that fluid dynamics was directly useful to a war machine. It is the mathematics of shells moving through air, of aircraft, of hydrodynamics. He was afraid that if his captors realized what he knew, they would force him to work on it, that his expertise would be turned into a weapon against his own country. So he hid it. He deliberately concealed the very thing that made him valuable, and in its place, inside a prisoner of war camp, cut off from libraries and colleagues and the world, he reinvented himself as a pure mathematician working on the most abstract subject he could find, algebraic topology, a field about as far from artillery shells as it is possible to get. He even organized a kind of university among the prisoners and made himself its rector. And out of that act of intellectual camouflage, out of a man hiding his real genius so it could not be used to kill, came some of the most important ideas in 20th century mathematics. Sheaf theory, spectral sequences, tools that now sit at the foundation of vast areas of modern math and physics. He built them in a cage to keep from being useful to the people who had put him there. Sit with the parallel for a moment, because I promised you the human stories in this subject are not decoration. They are the emotional structure of the thing itself. Jean Laray's great gift to fluid dynamics was the recognition that you sometimes have to give up smoothness, give up perfect regularity in order to survive, in order to guarantee that a solution exists at all. And then he spent 5 years of his life giving up his own smoothness, his own natural shape as a fluid dynamicist, hiding it, roughening himself into someone else, in order to survive a camp and deny his knowledge to an enemy. The man who taught the world that a solution can persist through singularities persisted through the worst singularity of the century by becoming, deliberately, something other than what he was. The personal and the mathematical are not two threads here. They are one thread running in both directions. Leray survived. He was liberated in 1945, returned to France, had a long and honoured career, and died on the 10th of November 1998, 3 days after his 92nd birthday. But the question he opened in 1934 outlived him, and it is still open, and now I need to make you feel exactly why it is so hard, because the difficulty is not vague. It is sharp and specific, and once you see it, you cannot unsee it. Let me give you the simplest possible version of blow-up, stripped of all the fluid machinery, so you can feel the mechanism in your hands. Forget water for a second. Consider one of the simplest equations a student ever meets, an equation that says the rate of change of a quantity equals that quantity squared. In symbols, the rate of change of y equals y times y. This is a nonlinear equation, in miniature, because the quantity feeds on itself, its growth rate depends on its own value squared. Now start it at the value 1 and let it run. What happens is not gentle growth. What happens is that the solution is 1 divided by the quantity 1 minus time. And watch what that does. At time 0 it equals 1, fine. As time climbs toward 1, the bottom of that fraction, 1 minus time, shrinks toward 0, and the whole quantity screams upward. At time exactly equal to 1, the denominator hits 0 and the value becomes infinite. Not large. Infinite. In finite time. The solution existed, it was smooth, it was perfectly well behaved, and then at a specific finite moment it destroyed itself by running to infinity. That is blow-up. And the reason the Navier-Stokes equation is so frightening is that its nonlinear term has, roughly speaking, exactly that self-squaring character. The velocity is transported by the velocity. The motion feeds on the motion. In the simple toy equation, nothing opposes the runaway, so of course it blows up. In Navier-Stokes there is an opponent, viscosity, the smoothing friction, standing against the runaway, trying to bleed the energy away before it can concentrate to a point. And the entire unsolved problem, the million-dollar question, the thing Leray could not settle and no one has settled since, is simply this. In 3 dimensions, does viscosity always win? Or can the nonlinear self-concentration, under some starting condition we have not thought of, outrun it and drive a real fluid to infinite velocity in finite time? There is a way of stating the problem that makes the knife edge of it very sharp, and I want to give it to you because it is the version the mathematicians actually carry in their heads. It is not true that we know nothing. We can prove something, and the thing we can prove is almost worse than knowing nothing, because of exactly where it stops. We can prove that if you start a 3-dimensional fluid off with a smooth condition, a smooth solution exists and stays perfectly smooth for at least a little while. A short time. This is called local existence, and it has been known for a long time, and it is solid. Give the equation a nice start and it behaves, guaranteed, for some finite stretch of time afterward. The trouble is the word finite. What the mathematics gives you is a guarantee of smoothness up to some time. Call it t. And then the guarantee runs out, and nobody can prove what happens at t. Maybe t is infinity, and the smooth solution simply lasts forever, and everything is fine, and the equation never breaks. That is option A, the safe universe. Or maybe t is a specific finite moment, an actual instant on the clock, at which the smooth solution can no longer be continued, because at that instant the velocity or its gradients have run to infinity. That is blow up. That is option B, and the entire clay problem, the whole $1 million, the 90 years of failure, comes down to this. We can prove the smooth solution exists up to time t. We cannot prove that t is always infinity. We cannot rule out that there is some innocent-looking starting condition whose t is a finite number, a specific afternoon on which a smooth, ordinary fluid tears a hole in its own description. The local theory hands you a smooth solution and a countdown clock, and it refuses to tell you whether the clock ever actually reaches 0. That is why the problem is called existence and smoothness. It is asking whether the smoothness we can guarantee locally can be extended globally to all time, or whether the countdown can hit 0. And this is the exact place where the 2 dimensions we do not live in, and the 3 dimensions we do part ways. In 2 dimensions, Ladyzhenskaya proved the countdown never reaches 0. T is always infinity. The clock is a fiction. The smooth solution runs forever, and you can throw it away. In 3 dimensions, the clock is real, and nobody has ever been able to prove it does not. For some starting condition, tick all the way down. You would think this would be easy to settle. It is not. And here is the first hint of why, the thing that should genuinely disturb you, and that we are going to spend the rest of this deep dive unpacking. In 2 dimensions, we know the answer. In a flat 2-dimensional world, a fluid governed by these equations can never blow up. It was proven. Viscosity always wins, smoothness always survives, the solution exists and is unique and stays beautiful forever. 2 dimensions is safe. Solved, closed, we do not live in 2 dimensions. In 3 dimensions, the exact same question, with the exact same equation, is completely open. Not hard. Open, unknown, unproven, in either direction. And the reason the answer changes when you add a single dimension, the reason our world, the 3-dimensional one, is the dangerous one, is a mechanism that simply does not exist in 2 dimensions. It is called vortex stretching, and it is the closest thing this story has to a monster. To understand it, and to understand why the person who cracked the two-dimensional case is one of the most extraordinary human beings in this entire history, I have to take you to the Soviet Union, to a family destroyed by Stalin, and to a woman who was forbidden from even attending university, and who solved in 2 dimensions the problem that the free world's finest minds could not solve in. 3. Her name was Olga Alexandrovna Ladyzhenskaya, and she was born on the 7th of March 1922 in Kolmogorov, a tiny town in the Russian forest, hundreds of kilometers from anywhere, near a river called the Unja. Her family had been minor nobility, which in the Soviet Union of the 1920s and 30s was not a heritage, it was a target. Her father, Alexander Ivanovich Ladyzhensky, was a mathematics teacher and a school principal, and by every account he was the person who lit the fire in her. He taught his daughters geometry himself, starting when Olga was a small child. He gave her the thing that would define her whole life. And in October of 1937, at the height of Stalin's Great Terror, the secret police, the NKVD, came for him. He was arrested and executed as an enemy of the people. The best evidence is that he was killed in an NKVD facility in the last week of October 1937. There was no trial that meant anything. There was no crime. He was a school teacher from a family with the wrong ancestry, in a year when the state was killing such people by the hundreds of thousands. It would be 19 years before he was formally exonerated, in 1956, after Khrushchev's secret speech denounced Stalin's crimes, and by then he had been dead for 2 decades. Think about what this did to the shape of Olga's life. Because she was now the daughter of an executed enemy of the people, doors closed all over the country. She finished high school in 1939 with the ability and the passion to study mathematics at the highest level, and she was barred from Leningrad University, not because she failed an exam, because of who her father had been. The state that had murdered her father then denied her the education that had been his gift to her. She went back to Kolmogorov and taught in a school. The way he had, her family survived those years by making things to sell: dresses, shoes, soap, the ordinary desperate economy of people the regime had marked. She would not be able to properly present her doctoral work until after Stalin died in 1953. The entire arc of her early career was bent and delayed and nearly broken by a political machine that had nothing to do with mathematics and everything to do with power. And she was, through all of it, magnificent. She eventually made it to Moscow State University, then to Leningrad, and she became one of the towering figures of 20th century mathematics, the leader of a whole school of thought on partial differential equations. She was friends with the distant writer Alexander Solzhenitsyn. The great poet Anna Akhmatova dedicated a poem to her. She was on the shortlist for the Fields Medal in 1958, the highest honour in mathematics, and in that same year, 1958, she published the result that puts her at the centre of our story. In a paper in the Soviet journal Doklady, volume 123, she proved the global unique solvability of the Navier-Stokes equations in 2 dimensions. That is the theorem I told you about. That is the proof that in a 2-dimensional world, fluids never blow up. She showed that in 2 dimensions, for any smooth starting condition, a smooth solution exists, it is unique, and it continues. Beautifully behaved for all time. She closed the 2-dimensional case completely. She took the wound Leray had opened, and in 2 dimensions, she stitched it shut forever. Her 1969 monograph, The Mathematical Theory of Viscous Incompressible Flow, became the foundational text of the entire field, the book everyone who works on these equations still traces their lineage back to. And here is a detail that I cannot get out of my head. When Ladyzhenskaya began working on the Navier-Stokes equations, she did not know about Leray's work, or Hopf's. She was behind the Iron Curtain, cut off, working in a scientific world that Stalin had sealed off from the West. She and Jean Leray were, without knowing the other existed, working on the same equation, the same wound. From opposite sides of a divided world, Leray, who had hidden his fluid dynamics from the Nazis in a prison camp, Ladyzhenskaya, whose father the Soviets had shot and who had been barred from university for it. Two people whom the two great totalitarian catastrophes of the century had personally marked, both drawn to the same quiet question about the mathematics of water. They only met after Stalin died, when Leray travelled to Leningrad and the two of them realised they had been reaching for the same thing all along, from inside two different cages. If you wanted to invent that, you couldn't. It is too much. It is real. But now I have to take away the comfort of her theorem, because the comfort is exactly what makes the rest of this so unsettling. Ladyzhenskaya solved 2 dimensions. She and everyone who came after her have completely failed to solve 3, and the gap between those 2 facts is not a matter of a slightly harder proof. It is a matter of a genuine physical monster that exists in 3 dimensions and simply cannot exist in 2. This is the thing I have been promising you. This is vortex stretching. In 2 dimensions, imagine the fluid as a flat sheet, and imagine a little whirlpool in it, a vortex spinning. In a flat world, that vortex can spin faster or slower, but it cannot do the one thing that makes 3 dimensions dangerous. It cannot stretch along its own axis, because in a 2-dimensional world, there is no axis to stretch along. The axis of a 2-dimensional vortex points straight out of the plane into a 3rd dimension that, in this flat world, does not exist. So the vortex is trapped. Its spinning is conserved. It cannot amplify itself. Mathematically, this is why 2-dimensional flow is tame. The quantity that measures local spinning, the vorticity, is simply carried along by the flow and cannot grow without bound. There is a ceiling, and the ceiling holds. Now go to 3 dimensions. Now the vortex is not a flat little whirlpool, it is a tube, a filament of spinning fluid, like a tiny tornado, with a real axis pointing in a real direction. And in 3 dimensions, the flow can grab that tube and stretch it. And here is the terrible part. The part that comes straight out of the physics of spinning objects. When you stretch a spinning tube of fluid, when you make it longer and thinner, it has to spin faster. It is the same reason a figure skater spins faster when she pulls her arms in. Conservation of angular momentum. Pull the mass inward, toward the axis, and the rotation rate climbs. A stretching vortex tube is a fluid pulling its own arms in. It gets thinner, and it spins faster, and as it spins faster it can stretch neighbouring tubes, which get thinner and spin faster still, and you have the beginnings of exactly the runaway feedback loop that the simple squaring equation showed us. Concentration feeding concentration. The velocity gradients climbing toward the sky. In 2 dimensions, this mechanism is simply absent. There is no axis, so there is no stretching, so there is no runaway, so there is no blow-up, so the problem is solved. In 3 dimensions, vortex stretching is real, and it is exactly the engine that could, in principle, drive a smooth fluid to a singularity. And the whole million-dollar question is whether viscosity, the smoothing friction, can always bleed away the energy fast enough to stop the stretching from running all the way to infinity. In 2 dimensions, the answer is yes. Provably, in 3 dimensions, the dimension you are sitting in right now, breathing 3-dimensional air, pumping 3-dimensional blood, nobody on Earth knows. There is a deeper way to say why 3 dimensions is so much worse, and it is worth the effort because it is the real technical heart of the problem, and almost no popular account will give it to you straight. It has to do with a property called scaling. The Navier-Stokes equations have a symmetry. If you take any solution and you zoom in on it in a particular coordinated way, shrinking space and time and rescaling the velocity altogether by matched amounts, you get another valid solution of the same equations. The equation looks the same at different scales. Now, mathematicians control equations using quantities that are conserved or bounded, things they can get a firm grip on. And for Navier-Stokes, the great controllable quantity is energy. The total kinetic energy of the fluid is bounded. Viscosity guarantees it can only decrease. That is the one solid handhold everyone has. And here is the catastrophe, stated as plainly as I can state it. In 3 dimensions, when you do that zooming in, that rescaling toward the small scales where a singularity would form, the energy does not stay the same size. It shrinks. The one quantity we can control becomes weaker and weaker exactly as we zoom into the region where the danger lives. By the time you are looking at the tiny scales where blow-up would happen, your control has evaporated. The mathematicians have a word for this. They call 3-dimensional Navier-Stokes supercritical. It means the tools we have are too weak, by a definite and measurable amount, to reach the scales where the equation might destroy itself. In 2 dimensions, the same calculation comes out balanced, critical, the energy exactly strong enough to hold the line, which is precisely why Ladyzhenskaya could win there. In 3 dimensions, the energy comes up short. It is not that we have not been clever enough, it is that our single best handhold is, provably, in the wrong place. The one rope we have does not reach the bottom of the well. That word, supercritical, is going to become the villain of the second half of this story, because in 2014, one of the greatest living mathematicians took that abstract sounding property and turned it into something close to a proof that the standard approach to this problem is doomed. Not hard. Doomed, but before we get there, before we reach the modern frontier where the smartest people alive are throwing supercomputers and artificial intelligence at this thing and still coming up short, I need you to understand the scale of what is being risked here. Because this is not a game. This equation is not a museum piece. Right now, as you listen to this exact unproven equation, with its unclosed wound and its unreachable scales, is being used to keep 400 people in the air over the Atlantic Ocean, and the engineers doing it know that no one has ever proven it can't break. I want to make the scale of that dependence concrete, because I think it is easy to hear the phrase used every day and let it slide past. Every commercial aircraft in existence was designed by solving the Navier-Stokes equations over and over on computers to work out how air flows over the wings and the fuselage and through the engines. The whole discipline is called Computational Fluid Dynamics, CFD, and it is a multi-billion-dollar pillar of modern engineering. Every car body shaped in a wind tunnel and then refined on a computer. Every ship's hull. Every gas turbine and jet engine. Every pipeline carrying oil or gas across a continent. The cooling of the microchips inside the device you are using right now. Artificial heart valves. Arterial stents. The dispersal of pollutants. And, on the largest scale of all, the weather forecast you checked this morning and the climate models that inform the future of the species. Every one of them is the Navier-Stokes equations, solved numerically, billions upon billions of times a day, across the entire industrial world. And all of it rests on an equation that we cannot prove has solutions. Now, an engineer will tell you, quite reasonably, that this does not keep them up at night, and they are right not to lie awake, because in practice the equation works with almost miraculous reliability. The planes do not fall out of the sky, the forecasts are usually decent. But I want you to notice the exact shape of the reassurance, because it is a strange one. The reassurance is that it works. It is not that we understand why it always works, or that we have proven it always will. It is empirical. It is the reassurance of the pre-scientific craftsman, of exactly the British bridge builders that the French committee praised over Navier. It works because it has worked. And the thing about the Navier-Stokes problem, the thing that the $1 million prize is really about, is that whether it always works, whether there is some unlucky configuration of a real fluid that sends the equation into a singularity, is precisely the question no one can answer. We have built our civilization on top of a mathematical structure whose soundness is formally unknown, and we have papered over the gap with the fact that so far, nothing has broken in a way we noticed. And the reason the gap has never been closed, the reason CFD is an art of approximation rather than a solved science, has a name, and the name is turbulence. Turbulence is the physical face of everything we have been discussing. It is what the runaway looks like when it does not quite run all the way to infinity. It is the wild, chaotic, swirling, unpredictable motion of a fluid at high speeds. The churn behind a fast boat, the roil of a river over rapids, the buffeting of an aircraft in rough air, the plume of smoke that rises smoothly from a candle for a few centimeters, and then, at some invisible line, shatters into chaos. That transition from smooth flow to turbulent flow happens uncountable trillions of times a day all over the Earth. And we cannot predict from first principles exactly where it will happen or what the turbulence will do once it starts. Turbulence is, without much exaggeration, the great unsolved problem of classical physics. The best way to see the enemy is to watch it appear, and the person who first watched it appear under controlled conditions was an English engineer named Osborne Reynolds, working in Manchester in 1883. His experiment is one of the most beautiful in the history of physics, because you can picture every part of it. He took a long glass tube and ran water through it, and into the centre of the flow, through a fine nozzle, he injected a thin thread of coloured dye. At low speeds, something lovely happened. The dye ran down the middle of the tube as a single clean, straight, unbroken line, a coloured thread suspended in clear water, perfectly steady, because the water was moving in smooth parallel layers that never mixed. He called this direct motion. We call it laminar flow. And then, slowly, he opened the valve and let the water move faster, and he watched the thread. And at a certain speed, quite suddenly, the thread of dye stopped being a thread. It wavered, it wobbled, and then it burst apart into a chaos of swirls and eddies that filled the whole tube and mixed the dye into the water completely. He called this sinuous motion. We call it turbulence. What Reynolds discovered was that the transition did not depend on the speed alone, or the width of the tube alone, or the thickness of the water alone, but on a specific combination of all of them, a single dimensionless number that we now call, in his honour, the Reynolds number. And below a certain value of that number, roughly 2000 to 2400 in a pipe, the flow is smooth and orderly and the dye stays a thread. Above it, the flow breaks into turbulence. The same transition you can see any time you turn a tap slowly and watch the water go from a clear glassy column to a frothing white chaos. The same transition in the smoke rising off a candle, smooth and laminar for the first few centimetres, then shattering into turbulent curls. That threshold, that sudden and total change in the character of a fluid at a critical value of a single number, is the visible face of the nonlinear term winning its tug of war against viscosity. And more than a century after Reynolds watched his dye come apart in a glass tube, we still cannot predict, from the equations alone, exactly when and how and into what precise pattern a given flow will make that jump. We can see it, we cannot compute it. And the people who understood physics most deeply have said so, in words that reveal something close to awe and something close to despair. Richard Feynman, in his famous lectures on physics in the early 1960s, called the problem of turbulent. Circulating fluids the most important unsolved problem of classical physics. He pointed out that it was a problem more than a century old that had defeated everyone, that here was ordinary matter, water and air, doing ordinary things, and the greatest minds could not write down what it was doing. There is an even more revealing quote from the British physicist Horace Lamb, who wrote the definitive textbook on hydrodynamics, and who, in an address to a scientific meeting around 1932, near the end of his long life, is reported to have said something like this: "I am an old man now, and when I die and go to heaven there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is the turbulent motion of fluids. And about the former I am rather optimistic." Read that again. This is one of the fathers of fluid dynamics saying, at the end of his life, that he expected to understand the quantum theory of light and matter, the most notoriously strange theory in all of science, before he expected to understand water going down a drain. There is a similar story told about Werner Heisenberg, one of the architects of quantum mechanics, who is said to have joked that he would ask God two questions: why relativity and why turbulence, and that he really believed God would have an answer to the first. I want to be careful and honest with you here, because this audience deserves it, and because it matters. The Heisenberg line is almost certainly apocryphal, a story that has been told so many times it has become true by repetition, and the exact wording of the Lamb and Feynman quotes varies from source to source. But the sentiment behind all of them is completely real and completely documented, and it is this: the people who cracked the atom, who unlocked the stars, who built the mathematical machinery of the quantum world, looked at a flowing fluid and admitted they were beaten, not because they were being modest, because it is genuinely, structurally, one of the hardest problems human beings have ever tried to solve, and it is hard for exactly the reason we have been building toward this whole time. The nonlinear term, the self-feeding, self-concentrating, scale-cascading term that Navier stumbled into, and Stokes formalized, and Leray could not tame. Let me show you why turbulence is computationally hopeless, because the numbers here are genuinely staggering, and they connect directly to the blow-up problem. When a fluid becomes turbulent, its energy organizes itself into swirls, eddies, across an enormous range of sizes at once. There are big eddies, and inside them, smaller eddies, and inside those, smaller ones still, all the way down. Energy pours in at the large scale, the scale of the wing or the river, and it cascades downward, eddy feeding smaller eddy, until at the very smallest scale the eddies are tiny enough that viscosity can finally grab them and turn their motion into heat. This picture, the energy cascade, was captured in a famous piece of doggerel by the meteorologist Louis Fry Richardson. Riffing on an older rhyme about fleas, big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. That is not just a poem, that is the physics. And in 1941, the Soviet mathematician Andrei Kolmogorov turned that picture into precise, testable predictions about how energy is distributed across the scales in turbulent flow. Predictions that have held up in experiment after experiment for 80 years and form the backbone of our understanding of turbulence. But Kolmogorov's own theory contains the seed of why we cannot simulate it. Because the range of scales in a turbulent flow, the ratio between the biggest eddies and the smallest ones, grows explosively with the intensity of the flow, measured by a quantity called the Reynolds number. And the number of separate pieces of information you would need to fully describe a turbulent flow, the number of degrees of freedom, grows roughly like the Reynolds number raised to the power of 9/4. Let me make that real. The Reynolds number of the air over a cruising passenger jet's wing is somewhere around 20 million. Raise 20 million to the power of 9/4, and you get a number of degrees of freedom that runs into the many trillions upon trillions. To directly simulate the turbulent air over a single wing, resolving every eddy down to the smallest, you would need a computational grid with a number of points that no computer on Earth can hold, and no computer on the foreseeable horizon will be able to hold. It is not a matter of waiting for faster chips. The scaling defeats you. Fully resolving the turbulence in real engineering flows by brute force is, for the important cases, permanently out of reach. Let me make that impossibility concrete, because the scale of it is genuinely difficult to hold in the mind. To directly simulate the turbulent air over a complete passenger aircraft, resolving every eddy down to the smallest scale where viscosity finally takes over. The most credible estimates put the number of grid points you would need at well beyond 10 to the 16th, and by some accounts far higher, each of them updated through millions of tiny time steps. This kind of brute force calculation, where you actually solve the true equations with no turbulence model at all, is called direct numerical simulation, and it exists, and it is real, and it is used in research, but it is confined to simple shapes and modest speeds, a box of turbulence, flow in a plane channel, and even those can consume months of runtime on some of the largest supercomputers on the planet. A full, direct, honest simulation of the air over a real wing at real cruising speed is not something we are waiting for a better computer to deliver next year. On the current trajectory of computing, it is centuries away, if it is reachable at all. The equation that designs the aircraft cannot be honestly solved for the aircraft. We have never once computed, from first principles, the true flow over the thing we trust it to keep in the air. And even if you could, there is a deeper problem waiting underneath. One that a meteorologist stumbled into by accident in the winter of 1961, and that broke the back of an entire dream. His name was Edward Lorenz, and he was running one of the earliest computer models of the weather, a stripped-down set of equations descended directly from the fluid equations we have been discussing. One day he wanted to re-examine a run, so he restarted it from the middle, typing in the numbers from a printout. The printout showed the values rounded to 3 decimal places, 0,506, when the computer had actually been carrying 6, 0,506127. A difference of 1 part in a few thousand, a rounding error smaller than the flap of an insect's wing against the whole weather of a continent, and the new run, starting from that almost identical number. Tracked the old one for a little while, and then diverged completely, until the two weather patterns had nothing whatsoever to do with each other. A microscopic difference in the starting condition had, in a short time, produced a totally different forecast. Lorenz had discovered what we now call chaos, sensitive dependence on initial conditions, and he published it in 1963 in the Journal of the Atmospheric Sciences in a paper called Deterministic Non-Periodic Flow. He later gave it the image that made it famous, asking whether the flap of a butterfly's wings in Brazil could set off a tornado in Texas. And what it means for our story is quietly devastating, even in the cases where the Navier-Stokes equations do have a nice solution. Even where nothing blows up and everything stays smooth, the flow can be so sensitive to its exact starting condition that any error at all, any rounding, any imprecision in your measurement of the initial state explodes into total unpredictability within a finite and often short time. The equation can be perfectly deterministic in principle and completely unpredictable in practice. This is why the weather forecast degrades past about a week, and why it will never, no matter how good our computers get, be reliable a month out. The determinism is real, and it is also useless, because you would need to know the present state of the atmosphere to infinite precision to use it, and you never can. So even the smooth, well-behaved, singularity-free solutions of this equation, the safe ones, the ones we are hoping are the only kind, refuse to be predictable. The equation guards its answers at both ends. Where it does not threaten to blow up, it threatens instead to become chaotic, to take the smallest uncertainty and amplify it without limit, until the future is a fog. So, what do engineers actually do? This is the part that I think should genuinely unsettle you, because it is the quiet admission at the heart of an entire field. They cheat. They do not solve the real equations. They cannot. Instead, they solve modified, averaged, simplified versions of the equations, in which the turbulence is not computed, but modelled, replaced by approximate formulas that are known by everyone who uses them, to be wrong in detail. The workhorse of industrial design is a family of methods that average the equations over time and then plug the gap, the missing turbulent stresses, with a model, a fudge, an educated guess dressed in mathematics. There are named models, the Kepsilon model, the Komega model, the Sparlat-Almaraz model. And each one is a different set of assumptions about turbulence that its own creators would tell you is an approximation with known failure modes. There is a more sophisticated approach that resolves the big eddies and only models the small ones, and it is better and far more expensive, and it too rests on modelling assumptions. None of it is the real equation. All of it works well enough, most of the time, for the specific situations it has been tuned and validated against. Say that back to yourself slowly. The single most important equation in engineering cannot actually be solved for the situations we most need it, so an entire global industry runs on approximations to it that are known to be false, calibrated against experiments, and trusted because they usually give answers close enough to reality that the planes stay up. It works, and nobody can fully explain why the fudges work as well as they do, and nobody can guarantee when they will fail, and the deeper question of whether the true underlying equation is even sound is left unanswered to the mathematicians, who have been unable to answer it for 90 years. This is not a scandal in the sense of a cover-up. Nobody is hiding it. It is worse than a cover-up. It is simply not talked about outside the field, so most people who fly, most people who trust the weather forecast, most people who benefit every single day from this equation, have no idea that at its foundation there is a question mark the size of a cathedral. You were never told, because the people who could tell you long ago stopped finding it remarkable. Familiarity did the work that suppression would have done. The gap is in plain sight and nobody looks at it. Which brings us, finally, to the year the mathematical world decided to stop looking away and put a bounty on the question and drew, one by one, some of the most brilliant people alive into a problem that has so far humiliated every one of them who has claimed to solve it. On the 24th of May in the year 2000, at a meeting held at the Collège de France in Paris, the Clay Mathematics Institute announced 7 problems. They called them the Millennium Prize Problems, and they attached to each one a bounty of $1 million. These were meant to be the 7 hardest, most important, most stubborn open questions in mathematics at the turn of the millennium, the problems whose solutions would define an era. And one of the 7 was the existence and smoothness of solutions to the 3-dimensional Navier-Stokes equations. The wound Leray opened in 1934, the danger Ladyzhenskaya sealed off in 2 dimensions, but not 3, was now officially one of the 7 great unconquered peaks in all of mathematics, sitting there alongside problems in number theory and topology and the foundations of computer science. The official statement of the problem was written by Charles Pfefferman, a mathematician at Princeton, himself a titan of the field, a man who won the Fields Medal at the age of 29. And I want to read you the spirit of how he framed it, because it is a remarkable admission coming from the institution of mathematics itself. He laid out precisely what would have to be proven in 3 dimensions for a fluid filling all of space or a repeating box, with no external forces and a nice smooth start. You would have to prove one of 2 things. Either option A, that a smooth solution always exists for all time with finite energy for every such starting condition, meaning the equation never breaks. Or option B, that there exists at least one smooth starting condition for which the solution breaks down in finite time, meaning blow-up is real and can be exhibited. Prove it never breaks, or find the case where it does. Either one wins the $1 million. And Pfefferman ended the official statement by acknowledging that our understanding of these equations is, in his words, at a very primitive level, that standard methods from the theory of differential equations appear inadequate to settle the problem, and that we probably need some deep new ideas. Deep new ideas. That is the establishment's own document, a formal problem statement, admitting that the entire existing toolkit of the field is not enough. Not that it is hard with current tools, that current tools appear inadequate, full stop, and that something not yet invented will be required. In the 26 years since, that assessment has been vindicated over and over, most brutally by the people who thought they had found the deep new idea and were wrong. Because before I show you the real frontier, I have to show you the graveyard, and it is worth spending time in the graveyard because it tells you how deep the trap is. In 2006, a mathematician named Penny Smith at Lehigh University posted a paper claiming a solution. Within a short time she withdrew it, having found, in her own words, a serious flaw. That is the honourable version, caught early, retracted quickly. The famous one is worse and stranger. In 2013 and 2014, a highly respected Kazakh mathematician named Mukhtar-Bey Otelbayev, one of the most eminent figures in Central Asian mathematics, published a paper claiming a full proof that the 3-dimensional equations always have smooth solutions. Option A, the whole prize. And this was not a crank. Otelbayev was a serious man with a serious reputation, and the mathematical world took it seriously. People all over the world, including Terence, whom you are about to meet properly, started digging through the argument line by line, and they found the flaw. It was on page 56. An inequality, numbered 6.34 in his paper, which he needed for everything downstream, did not actually follow from the inequality above it, numbered 6.33. The chain broke right there on one line on one page, and what happened next is the human heart of this whole graveyard. Otelbayev, confronted with the error, did not bluster or deny. In an email in February of 2014, he wrote, and I am quoting a man's private moment of professional devastation, "To my shame, on page 56, the inequality is incorrect, therefore the proposition is not proved. I am so sorry. To my shame, I am so sorry." This is one of the leading mathematicians of his country, who believed, genuinely, that he had solved one of the 7 great problems of the age, discovering in front of an audience of his global peers that he had made an error on line 6.34 of page 56. And I cannot help hearing, across nearly 2 centuries, the echo of Navier. The man of enormous ability, staking his reputation on the power of his mathematics, publicly, and being brought down not by a lack of brilliance, but by a single point of failure that the whole world could see. Navier's water main. Otelbayev's inequality 6.34. The equation seems to demand a kind of humiliation from the people who love it most. It lets them get almost all the way, and then it opens a crack, and the crack is small and precise and fatal, and everyone watches. Now, in between the graveyard of failed proofs, real progress has been made, and it is important. And it is also quietly terrifying in what it implies. Because the results that mathematicians can prove about this equation have a very particular flavour. They can prove things about how a singularity would have to look if it existed, without being able to prove whether it exists at all. In 1982, 3 mathematicians, Louis Caffarelli, Robert Cohn, and Louis Nirenberg, building on earlier work by Vladimir Scheffer, proved one of the deepest partial results we have. They showed that for a certain well-behaved class of weak solutions, if singularities exist at all, the set of points where they can occur is extraordinarily small. Smaller, in a precise mathematical sense, than a curve. The possible singularities cannot fill up a line in space and time. They have to be, at most, a scattering of isolated points, a dust, a set so thin it has zero measure in the relevant dimension. That is genuine hard-won knowledge. But look at its shape. It is a theorem about the geometry of a catastrophe whose existence remains completely unknown. It tells you the monster, if it is real, must be very small and very sparse. It does not tell you whether the monster is real. There is a whole family of results like this, and they all have the same haunted structure. There is a criterion, proved by Beale, Cato and Majda in 1984, that says a smooth solution can only break down if a specific quantity, the maximum spinning intensity of the fluid, the peak vorticity, integrated over time, runs to infinity. Control the peak vorticity, and you prevent blow-up. It is a beautiful result, and it converts the whole problem into a question about whether that one quantity can escape to infinity, and nobody can prove that it can't. There are the conditional regularity criteria associated with Ladyzhenskaya and Giovanni Prodi and James Serrin that say if the solution stays bounded in a certain precise way, then it must be smooth, and the very last, hardest borderline case of those criteria was only nailed down in 2003 by Escoriaza, Seragin and Verk, and even that leaves the main question wide open. Every one of these results is a fence built around the monster. We have built a very elaborate cage. We have specified with great precision exactly what the monster would have to look like and exactly what it would have to do to escape. We have never established whether there is a monster in the cage at all. And then, in 2014, Terence Dow, who is very possibly the most gifted mathematician alive, did something that changed the emotional temperature of the entire problem. He did not solve it. He did something almost worse. He proved, in a specific and rigorous sense, that the standard way everyone had been trying to solve it cannot work. To understand what Dow did, you have to remember the word supercritical, the property I told you would come back. The reason nobody can control three-dimensional Navier-Stokes is that our one solid handhold, energy, becomes weak exactly at the small scales where a singularity would form. Every serious attempt to option A, every attempt to prove the equation never breaks, has ultimately relied on energy, plus some clever additional inequalities, to try to keep control at those small scales. And the whole community had a nagging suspicion that this was hopeless, that energy was simply too weak, that you could never get there with these tools. Tao made that suspicion into a theorem. His paper, published in 2014 in the Journal of the American Mathematical Society, is called Finite Time Blow-Up for an Averaged Three-Dimensional Navier-Stokes Equation. And here is the strategy, which is one of the most ingenious pieces of mathematical judo I have ever encountered. Tao could not prove that the real equation blows up, so instead he built a fake one. He constructed a modified version of the Navier-Stokes equations, an averaged version, carefully engineered so that it obeys all the same fundamental properties that every existing proof technique relies on. It has the same energy identity. energy is controlled in exactly the same way. It has the same scaling, the same supercriticality, the same behavior under all the standard estimates. From the point of view of the entire conventional toolkit, his fake equation and the real equation are indistinguishable. Any proof of regularity that worked on the real one, using only those standard tools, would have to work on his fake one too. And then he proved that his fake equation blows up. In finite time, from smooth initial data. A guaranteed, rigorous singularity. Which means, and this is the devastating conclusion, that no proof using only the standard energy-based toolkit can possibly establish that the real equation is safe, because that exact same proof would falsely certify his blowing up imposter as safe too. He did not prove the real fluid explodes. He proved that the method everyone was using to try to show it doesn't is dead on arrival. He formalized the supercriticality barrier. He proved that Pfefferman's deep new ideas are not optional. The old ideas are not just insufficient, they are provably incapable. But it is the mechanism of Tau's blow-up, the actual physical picture of how his fake fluid destroys itself, that I have not been able to stop thinking about since I first understood it. Because it is not a smooth runaway, it is something that feels almost alive. Tau designed his equation so that the fluid could implement, in its own churning motion, something like a machine. A logical machine. He described it in terms of building blocks that behave like the gates in a computer circuit, and out of these fluid logic gates he assembled a structure that does one specific chilling thing. It is a self-replicating machine. A configuration of fluid energy that after a certain delay uses its own energy to construct a smaller, faster copy of itself at a finer scale, and then hands off all its energy to that copy and disappears, and the copy does the same thing. It builds a copy of itself smaller and faster still, and hands off, and vanishes, and that one does it again. Do you see what that is? It is a cascade with a purpose. Each generation of the machine is smaller than the last by a fixed ratio, and faster than the last, and it builds its successor before it dies. So the machine climbs down the scales from large to small to smaller to smaller still, faster and faster at each step, and because each step takes less time than the one before, the whole infinite sequence of steps, an infinite number of generations of self-replicating fluid machine, completes in a finite total time. And at the end of that finite time, the energy has been driven into an infinitely small, infinitely fast point. The fluid has blown up. Not by accident, by construction, by a self-replicating automaton built out of moving water, driving itself toward its own singularity, one generation at a time. The science writers at Quantum magazine compared it to the cat in the hat, who pulls a smaller cat out of his hat, who pulls a smaller cat out of his, all the way down. It is a perfect image, and it is also, when you sit with it, one of the strangest ideas in modern mathematics. A fluid that computes its own destruction. And here is the part that Tao himself has pointed toward, half seriously and half as a genuine research program. That I find genuinely difficult to hold in my mind. His averaged equation was designed by hand to allow that machine to exist. The real Navier-Stokes equations were not designed by anyone. The question Tao effectively raised is whether the real equations of real water and real air are rich enough as a computational medium to support a machine like that on their own. Whether you could, in principle, program ordinary fluid, the way you program a computer, to build a self-replicating structure that drives itself to a singularity. He suggested that the missing piece is not really a mathematical obstacle in the usual sense, but something closer to an engineering problem, the problem of building reliable logic gates out of an ideal fluid, of getting the fluid to compute robustly enough. If you could build a fluid computer, you could program the fluid to destroy itself, and the three-dimensional Navier-Stokes problem would fall in the direction of catastrophe. Option B. Blow up is real because we made the fluid do it on purpose. I do not know how seriously to take that as a practical route to a proof, and, honestly, neither does anyone else, which is part of why it haunts me. But as a way of understanding the character of this equation, it is perfect and it is disturbing. It says that the reason we cannot prove fluids are safe may be that fluids are not in fact safe, that the equation of everything that flows is powerful enough, expressive enough, to contain within its ordinary-looking terms the logical machinery of a self-annihilating machine. That the smoothness of water is not guaranteed by anything. It is just the way the machine happens not to have been programmed yet. And if you think that is where the strangeness bottoms out, that the worst the equation can do is possibly, maybe, under some exotic engineered condition, blow up, then you have not yet heard about what happened to the concept of a unique answer. Because over the last decade, a group of mathematicians took the weak solutions that Leray invented, the rough smeared out solutions he built to guarantee existence, and they proved something about them that strikes at something even more fundamental than blow up. They struck at determinism itself. Here is what determinism means for a classical equation, and why it is supposed to be sacred. If you know the exact state of a fluid right now, every velocity at every point, then the equation is supposed to tell you the exact state at every future moment. One present, one future. That is what it means for physics to be deterministic. Give the universe a starting condition, and it has no choice about what happens next. The entire classical worldview, the clockwork universe, rests on the idea that the equations have unique solutions, same input, same output. Always, starting around 2017, Tristan Buckmaster and Vlad Vicol, using a powerful and relatively new technique called convex integration, which had been developed by Camillo de Lellis and Lessel Skelly-Heady and used to crack an old conjecture about the Euler equations, proved that the weak solutions of the three-dimensional Navier-Stokes equations are not unique. They constructed, rigorously, situations in which a single fluid, with finite energy, satisfying the equation in Leray's weak sense, can evolve into more than one future. Same starting condition, different outcomes, both of them legitimate weak solutions of the same equation. The clockwork does not have one setting, it has many. And you cannot predict which one nature will pick, because as far as the weak equation is concerned, they are all equally valid. Now, I have to be scrupulous here, because this is exactly the kind of place where a less careful telling would overreach, and you deserve the precise truth. These non-uniqueness results are about weak solutions, the rough ones, not about the smooth classical solutions that the clay problem is really about, and some of the strongest results require an external force driving the fluid. In 2022, Dallas Albritton, Elia Brew, and Maria Colombo published a paper in the Annals of Mathematics, the most prestigious journal in the field, proving non-uniqueness even for Leray's own class of solutions, for the forced equations. They exhibited two genuinely different Leray solutions arising from the very same starting state, the fluid perfectly at rest, zero velocity everywhere, driven by the same force. From nothing, from stillness, two different fluid histories, both obeying the equation. They built it out of an unstable swirling vortex, following a scenario that had been predicted years earlier by Hao Jie and Vladimir Virk, who had suspected that the seeds of non-uniqueness were hiding inside the instability of certain special flows. The reason I am careful to tell you these are weak and often forced solutions is not to diffuse the strangeness. It is because the strangeness survives the caution. Because the whole reason weak solutions exist at all is that we cannot prove the smooth ones do. Leray built the weak solutions as a lifeboat, a weaker notion of solution we could guarantee, precisely because the strong ones might blow up, and now we have learned that the lifeboat leaks. The weaker notion of solution, the one we retreated to when we could not control the real one, turns out to be non-deterministic, capable of giving contradictory answers to the same question. So the situation is this. We do not know if the smooth solutions always exist. When we retreat to the weak solutions to be safe, we find that they are not unique, that they violate the determinism we thought was the whole point. The equation refuses to be pinned down at both ends. Ask it for smoothness, and it may hand you a possible singularity. Ask it instead merely for existence. Accept roughness, and it may hand you a fork in reality. Two futures from one past. There is no version of the question we know how to ask this equation that gives back the clean, single, guaranteed answer that we assumed for 200 years it was quietly providing all along. That is the state of the mathematics. And I want to be honest that when I first fully understood it, I had to put the papers down and go for a walk. Because the thing I had assumed my whole life, that the ordinary physics of ordinary water was a closed book, a solved and boring and safe corner of science, was not just unproven, it was unproven in a way that reached down and touched determinism and infinity and the basic question of whether our best description of the physical world even has answers. And the frontier, the place where the smartest people alive are pushing right now. In the last 3 years, with computers and with artificial intelligence, has only made the picture sharper and, in a way I will try to be careful about, more frightening. For a long time, the search for blow-up focused on a slightly different equation, the one we started with, Euler's frictionless equations from 1755. Remember, Euler is Navier-Stokes with the viscosity switched off, with the smoothing friction removed entirely. And you might think that removing the one force that opposes the runaway would make blow-up easy to prove. It did not for a very long time, but it did make it a more promising place to look, because without viscosity fighting back, the self-concentrating nonlinear term has nothing standing in its way except the geometry of the flow itself. In 2013, two mathematicians, Thomas Howe and Guo ran an enormous, careful computer simulation of the Euler equations for a swirling flow inside a cylinder up against a boundary wall, and they found what looked, for the first time, like a clean, convincing, finite time singularity. The numbers screamed toward infinity in a controlled, self-similar way, right at the boundary. It was numerical evidence, not proof, but it was the most compelling blow-up scenario anyone had ever seen, and it pointed to the wall, the boundary, as the place where fluids are most dangerous. And then, over the following decade, Ho and his collaborator Jiaji Chen did something that the field had almost stopped believing was possible. They turned that numerical evidence into a rigorous proof, using what is called a computer-assisted proof, where the computer does not just simulate the flow, but rigorously bounds every source of error, tracking the mathematics with certified provable precision rather than mere approximation. They proved, and this was finalized in a paper that appeared in the Proceedings of the National Academy of Sciences in 2025, that the three-dimensional Euler equations, with a boundary, with smooth initial data, genuinely produce a finite time singularity. Real blow-up. Proven, reviewed by the leading figures in the field, including Tao himself. After decades of the monster staying hidden, someone finally proved that in at least one fluid equation, a close cousin of Navier-Stokes, the monster is real. I have to stop you from overreading this, because the caveat is the whole point, and I would be lying to you if I let the triumph stand unqualified. This is the Euler equation, not Navier-Stokes. It is the frictionless one, the one with the smoothing force removed, and it required a boundary, a wall, to make the singularity form. The actual Clay problem, the one with $1 million on it, is about the full Navier-Stokes equations, with viscosity present, fighting back, and in the pure setting without boundaries. That problem is still open. Chen and Hao did not solve it. What they did was arguably more psychologically important than that. They proved that finite time blow up in a real, three-dimensional, physically meaningful fluid equation is not a fantasy. The monster exists. It has been photographed, so to speak, in a closely related species, which makes the possibility that it also lives in the true Navier-Stokes equations feel less like a paranoid mathematical worry and more like a matter of time, and the tools that are now closing in on it are genuinely new, in exactly the way Pfefferman said would be necessary. In 2022, Tristan Buckmaster, together with Gonzalo Cao-Labora and Javier Jamez Serrano, proved the existence of smooth imploding singularities for compressible fluids, including, for the first time, a version of the compressible Navier-Stokes equations, a fluid collapsing in on itself in a perfect self-similar implosion. Thomas Howell, in 2024, produced numerical evidence of nearly self-similar blow-up in a modified, generalized version of the axisymmetric Navier-Stokes equations, with the peak vorticity climbing to values on the order of 10 to the 30th power, an unimaginable concentration, closing in on the true equation from yet another direction. The circle is tightening. Every year, the modified equations that blow up look a little more like the real one. And then, in 2025, artificial intelligence entered the story, and it entered in a way that I think genuinely marks a turning point, though I want to be careful about exactly what kind of turning point it is. A large collaboration of more than 20 researchers, working with Google DeepMind, used a technique called physics-informed neural networks, machine learning systems trained to satisfy the fluid equations directly, to hunt for singularities in the Euler equations and several related fluid models. And they found new ones. They discovered whole new families of singularity solutions that no human being had ever found, including, crucially, unstable ones. This matters more than it might sound. For years, the reason people gave for why we never see these singularities in real life, and why they are so hard to find, is that the important ones are unstable, meaning the tiniest perturbation knocks the fluid off the path to the singularity, so they hide from both experiment and computation. The AI found them anyway. It found the hidden, unstable, needle-balanced solutions that human methods could not reach, and it found them with a numerical precision so extreme that the leading experts started talking about using them as the seeds for the next generation of rigorous computer-assisted proofs. Charles Pfefferman, the man who wrote the official Clay problem statement in 2000, the man who declared that we would need deep new ideas, commented on this new AI-driven work, and what he said should stay with you. He noted that a lot of people believe the singularities are there, but that they are unstable, so we never see them, and that the discovery of these unstable singularities means their instability no longer prevents us from finding them. And on the prospect of finally turning these AI-found solutions into a rigorous proof of blow-up, he said something I find quietly momentous coming from him. He said the AI solution is quantitative and precise and has a much better chance of being made rigorous, that now there is a roadmap toward a proof, that it will take a lot of work, but, in his words, I do not see that it will take genius. I think it is doable. Doable, after 90 years, from the man who literally defined the problem, the word is doable. Not solved, not close, exactly, but for the first time, someone who understands this problem as well as any human alive is looking at a path and saying he can see the far end of it. Javier Jamez Serrano, one of the central figures in this new wave, is scheduled to give a lecture in early 2026 titled, simply, Navier-Stokes, Existence or Breakdown. Existence or Breakdown. option A or option B. The whole 200-year question compressed into 3 words, and the fact that a serious mathematician is willing to stand up and frame it that starkly tells you the field can smell that something is about to give, but it has not given yet. As of right now, in 2026, the Navier-Stokes existence and smoothness problem is open. The $1 million is unclaimed. Of the 7 Millennium Problems named in 2000, exactly one has ever been solved: the Poincare conjecture, cracked by the reclusive Russian Grigory Perelman, who then turned down the $1 million and the Fields Medal and walked away from mathematics entirely. The Navier-Stokes problem is not that one. It is still sitting there, exactly where Leray left it in 1934, exactly where Pfefferman framed it in 2000, a wound in the mathematics of the physical world that we have spent nearly a century unable to close. Closing in on now, maybe, from a dozen directions at once, but not closed. And I want to take you, in the time we have left, out of the mathematics and into what all of this actually means for you, sitting there, in your 3-dimensional body, breathing. Before we get to your body, I have to answer a question you should be asking, because it is the question that separates a mathematical curiosity from something that touches reality, and the answer is genuinely strange. The question is this: so what if the equation blows up? Real water does not move at infinite speed. Real air does not concentrate all its energy into a single point. If the mathematics predicts a singularity that the physical fluid clearly cannot produce, then who cares? Is this not just a sign that the equation is an imperfect model, and that the real fluid does something more sensible that the equation fails to capture? That is exactly the right question, and here is why the answer refuses to comfort you, no matter which way it breaks. There are only 2 possibilities, and they are both disturbing. Possibility 1 is that the equation is right, that blow-up is real, and that a genuine, physical, mathematical singularity can form in a fluid governed by these laws. If that is true, then reality itself, ordinary fluid reality, contains events where a smooth, finite, well-behaved state gives birth to infinity in a finite amount of time, out of nothing but its own internal dynamics. Not in a black hole, not at the beginning of the universe, in the equation that describes the coffee on your desk. Possibility 2 is that blow-up is real in the equation, but that real fluids do something else at that moment, that the physical fluid, as it approaches the singularity, reaches scales so small that the whole idea of a smooth continuous fluid stops being true. And this is the more likely resolution, and it is the one most physicists would bet on, but look carefully at what it actually says. It says that at the point where the mathematics predicts catastrophe, the model breaks. Because the Navier-Stokes equation treats a fluid as a perfectly smooth, infinitely divisible continuum, exactly as Stokes insisted in 1845 when he threw out Navier's molecules. But real water is not infinitely divisible. Zoom in far enough, down to scales of nanometers, and the smooth continuum dissolves into individual molecules bouncing around in mostly empty space, and the equation, which knows nothing of molecules, simply ceases to apply. So if blow-up is real in the equation, what it is really telling you is that the equation is driving itself, from a perfectly ordinary large-scale start down toward the scale where its own foundational assumption collapses. The singularity is the equation reaching down and touching the exact place where it stops being true. Sit with that, because it is subtle and it is worse than it first sounds. It means our single most successful description of the physical world may contain, hidden inside perfectly innocent starting conditions, a built-in mechanism that drives it toward its own breakdown. Not a breakdown we impose from outside, not an approximation we knowingly made, but an internal tendency of the equation to concentrate itself down to the scale where it invalidates itself. And we cannot find the starting conditions that do this. And we cannot prove they do not exist, and every day we solve this equation billions of times without knowing whether the particular flow we are computing is one of the safe ones or one of the ones quietly reaching for the floor. The engineering works because so far the flows we have needed have stayed in the safe regime, or close enough to it, or the numerical methods smear out the dangerous scales before they can form. But nobody has proven there is a safe regime. Nobody has drawn the line. We are computing on a surface without knowing where the edge is, and here is the thing that connects it to the largest structures in the cosmos. The thing I find genuinely vertiginous. Physics knows of only a very few places where it admits that its own equations produce true singularities, points where the mathematics gives back infinity and the description falls apart. One is the center of a black hole, where general relativity predicts the curvature of space-time becomes infinite. Another is the very first instant of the universe, the Big Bang, where the same theory predicts infinite density. These are treated as the deepest and most profound frontiers in all of physics, the places where our current laws are known to be incomplete, where we expect a deeper theory, quantum gravity, to eventually take over. They are spoken of with awe. They are the edges of knowledge. And the Navier-Stokes blow-up problem is asking whether that same category of event, a true mathematical singularity, an infinity born from finite smoothness, might be lurking not at the edge of a black hole or the birth of the cosmos, but in a bathtub, in a river, in the turbulent wake behind a swimming fish, in the same physics you are surrounded by and made of right now. Which is where I have to bring this home, because this was never really about aeroplanes or prize money or French bridges. It was always, in the end, about you and the fluid you are. You are, by mass, mostly water, and you are, by function, a collection of flows. Consider your own heart. Right now it is contracting a little more than once per second, and every time it does, it fires a jet of blood out through the aortic valve into the ascending aorta, the great trunk artery that arcs over the top of your heart, and that flow is fast. At the peak of each contraction, at peak systole, the Reynolds number in your aorta, the very quantity that measures whether a flow is smooth or turbulent, climbs to somewhere on the order of a few thousand. Past the threshold where flow is known to become unstable, to transition, to break from smooth laminar order into the beginnings of turbulence. Your blood does not flow through your largest artery like syrup down a clean pipe. At the peak of every heartbeat it churns, it swirls, it forms little vortices in the curve of the aortic arch, and then, as the pulse subsides, it settles. And then the next beat comes and it churns again. Your cardiologist relies on the Navier-Stokes equations, solved on computers, to model that flow, to design the artificial valves and the stents that might one day be placed inside you. And the equation they are using to model the blood in your chest is the same equation no one on Earth has been able to prove has solutions. Every heartbeat you have ever had, every heartbeat you will ever have, is a flow that the mathematics cannot fully guarantee it can describe. The turbulence in your own aorta, right now, this second, is an instance of the single most important unsolved problem in classical physics, running in real time, a few inches behind your sternum. And your body solves it. Effortlessly, without error, without ever once producing the infinity the mathematics is afraid of, billions of beats across a lifetime, your blood computes its own turbulent flow perfectly, obeying an equation we cannot solve, arriving instantly and continuously at the answer that the finest mathematicians of 2 centuries could not prove even exists. And it is not just your blood. Take a breath, right now, a real one, and pay attention to the air moving in through your nose or your mouth and down your windpipe. That flow too in the larger airways, at anything above a gentle breath, becomes turbulent. The air branching down into your lungs, dividing and dividing through the bronchial tree, is a fluid flow governed by these same equations. Every breath you take is turbulent flow. Every breath you take is, in the strict mathematical sense, an unsolved problem, computed flawlessly and instantly by nothing more than air obeying physics. You are, at this moment, breathing an equation that the human race cannot solve, and you have been doing it without a single failure since the moment you were born. Step back and look at the whole planet doing this. The weather over your city is Navier-Stokes. The jet stream, the hurricanes, the gentle turning of a breeze around a building, all of it, every moving parcel of air on Earth, is solving these equations continuously and without pause. Every river solving them, every ocean current, every wave, the entire circulation of the seas that regulates the climate of the world, all of it flowing in perfect obedience to a mathematical law whose solutions we cannot prove into existence. The universe does not appear to be waiting for us. It does not consult the mathematics. It does not check whether a solution exists before it lets the water move. It simply computes, everywhere, all at once, at every scale, the answer to the equation we have been staring at, defeated, for 204 years. And it never once returns an infinity, and it never once fails, and it never once tells us how it is doing it. That is the thing I cannot get past. Not the possibility of blow-up, the ordinary, everyday, wall-to-wall fact of the universe fluently solving, trillions of times per second, in every glass and every cloud and every artery, a problem that has humiliated the smartest members of our species for a century. We built a civilization on this equation by copying nature's answers, without understanding the method. The engineers are, all of them, in the deepest sense, in the position of Navier's British rivals that the committee praised, the empirical builders who trusted what worked over what could be proven. And the mathematicians are in the position of Navier himself, insisting that the truth must be provable, that the world must in principle be captured in rigorous mathematics, and being unable. After all this time, to close the gap between the equation that works and the proof that it should. Think about the people this problem has moved through. Navier, who wrote it down without understanding it, and whose bridge collapsed in the heart of Paris, immortalized by Balzac as the engineer who trusted the mathematics too much, dead at 51. His name cut into the Eiffel Tower, where no one reads it, and the paper written about him almost 2 centuries later, titled Blow Up and Collapse, as if the equation had reached back through time and named his life after itself. Stokes, in Newton's chair for 54 years, who understood the equation and gave it its foundation, and never dreamed that the foundation had a crack in it that would still be open in the 21st century. St. Venant, who may have gotten there first, and whom you had never heard of until an hour ago. Leray, who could only guarantee that the equation had any solution at all by giving up its smoothness, by accepting that it might, at certain instants, break, and who then spent 5 years in a prison camp deliberately breaking his own smooth shape, hiding the very knowledge we are discussing so that it could not be turned into a weapon. Ladyzhenskaya, whose father was shot by a state that then forbade her the education he had given her, and who from inside that cage reached out and closed the 2-dimensional case forever, sealing the wound in the one world we do not live in. Atelbaev, who believed he had it and found his error on page 56, and wrote to his colleagues, "To my shame, I am so sorry." Tao, who proved that the way everyone was trying could not work, and who imagines a machine made of water building smaller and faster copies of itself, all the way down to its own annihilation. Pfefferman, who wrote the problem and waited a quarter of a century, and now says, cautiously, that he thinks it is doable. Every one of them was reaching for the same thing. The guarantee that the world of moving fluids, the world you are made of, is mathematically sound. That there is no unlucky arrangement of water or air, no gust, no swirl, no heartbeat, that sends the equation, and maybe the fluid, into infinity. And not one of them has been able to give us that guarantee. It is still, tonight, an open question whether the physics of your own body is provably safe from producing a singularity, or whether it merely happens, so far not to have. And here is where I have to leave you, because there is no comfort at the bottom of this, and I am not going to invent one. There are two possibilities, and you have to hold both of them. Either the equation is complete and the singularity is real, and then reality, ordinary fluid reality, the reality of your blood and your breath and the rain, contains the same category of catastrophe as the center of a black hole, waiting, in principle, in conditions we have not found, to turn smoothness into infinity in finite time. Or the equation is subtly, deeply false in a way that hides itself perfectly under every ordinary condition, and only reveals itself at the scale where the whole model dissolves, and then our single best description of the physical world is a lie we have never been able to catch, running underneath every plane and every forecast and every beating heart, and we cannot find where it lies. The mathematics that describes the world either breaks or it lies, and after 204 years we still cannot tell you which. You will take roughly 20,000 breaths today. Each one of them is turbulent. Each one of them is a solution to an equation that no living person can prove has solutions. Your heart will beat about 100,000 times before this time tomorrow, and every single beat will churn your blood past the threshold into turbulence, and every single beat your body will solve, flawlessly and instantly and without explanation, the problem that a private institute in Massachusetts has offered $1 million to anyone who can merely prove is solvable at all. The money is still there, the question is still open, and the fluid does not wait for the proof. It never has. It moves through you tonight the way it moves through the rivers and the storms and the dark oceans, obeying a law we wrote down and cannot read, arriving at an answer we cannot reach, and it has never, not once in the history of the world, told a single one of us how.